The Lagrange mean value theorem (MVT) says, if a real valued function f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists at least one point c in a to b such that f prime of c equals f of b minus f of a divided by b minus. Geometrically, this means that the slope of the straight line joining the endpoints, the secant line, is exactly equal to the slope of a tangent line at some interior point. Imagine a road that climbs from altitude f of a at mile a to altitude f of b at mile b. The average steepness of the whole road is f of b minus f of a divided by b minus. The theorem guarantees that at some mile c the instantaneous steepness, the derivative matches that average. A typical graph shows a smooth curve from a f of a to b, f of b with a tangent drawn at c that is parallel to the secant line. Two technical requirements are needed. Continuity on a bracket a comma b bracket. The function must have no jumps or holes in the whole interval, including the endpoints. This ensures the secant line is well defined. Differentiability on a parenthesis a comma b parenthesis. The function must be smooth enough to have a finite slope at every interior point. The endpoints need not be differentiable because the theorem never asks for f prime of a or f prime of b. If either condition fails, the conclusion can break down. For example, f of x equals absolute x on bracket minus 1 comma 1 bracket is continuous but not differentiable at 0, and the average slope is 0, yet there is no point where the derivative equals 0. The left-hand derivative is minus 1, the right-hand derivative is 1. Conversely, a function with a jump, such as f of x equals piecewise 0 when x less than 0, 1 when x greater than or equal to 0 on bracket minus 1 comma 1 bracket, is not continuous, so the theorem does not apply. The proof starts by reducing the problem to Rolle's theorem. Define the auxiliary function g of x equals f of x minus fraction f of b minus f of a over b minus a times x minus a minus f of a. Observe that g of a equals 0 because the second and third terms cancel at x equals a and g of b equals f of b minus fraction f of b minus f of a over b minus a times b minus a minus f of a, which simplifies to f of b minus f of b plus f of a minus f of a equals 0. Thus g satisfies the hypotheses of Rolle's theorem. It is continuous on a to b, differentiable on a to b, and g of a equals g of b. Rolle's theorem guarantees a point c in a to b with g prime of c equals 0. Compute g prime of x equals f prime of x minus fraction f of b minus f of a over b minus a. Setting g prime of c equals 0 gives exactly f prime of c equals fraction f of b minus f of a over b minus a, which is the statement of the mean value theorem. The construction of g of x is the key step that turns a general secant slope into a situation where the endpoints are equal, allowing us to invoke Rolle's theorem. Explanation: several useful corollaries follow immediately from the MVT. Monotonicity: if f prime of x is greater than or equal to 0 for every x in open parenthesis a comma b close parenthesis, then for any a less than x1 less than x2 less than b we have f of x2 minus f of x1 equals f prime of c times open parenthesis x2 minus x1 close parenthesis greater than or equal to 0. By the MVT, so f of x2 is greater than or equal to f of x1. Hence f is non-decreasing. Similarly, f prime of x is less than or equal to 0 implies f is non-increasing. Existence of roots: suppose f of a times f of b is less than 0, the function takes opposite signs at the ends. If f is continuous on open bracket a comma b close bracket and differentiable inside, then the intermediate value theorem already gives a root. The MVT adds that there is a point where the derivative has the same sign as the secant slope, which can be used to bound how quickly the function crosses the axis. Bound on derivatives from f prime of c equals open parenthesis f of b minus f of a close parenthesis divided by open parenthesis b minus a close parenthesis. We obtain absolute value of f prime of c is less than or equal to open parenthesis max sub open bracket a comma b close bracket of f minus min sub open bracket a comma b close bracket of f close parenthesis divided by open parenthesis b minus a close parenthesis. Thus, the maximum absolute derivative on the interval cannot exceed the overall change divided by the length of the interval. This inequality is often used to estimate errors in numerical methods. The MVT is a powerful tool for proving inequalities. For example, let f of x equals sin x on 0 to x with x greater than 0. The function is continuous and differentiable, so there exists c in 0 to x such that sin x minus sin 0 equals cos c times x minus 0. Since cosine c magnitude less than or equal to 1, we obtain sine x magnitude less than or equal to x magnitude, which is a classic bound for small angles. A similar trick works for the natural logarithm. Take f of t equals ln of 1 plus t on 0 to x with x greater than minus 1. ln of 1 plus x minus ln 1 equals 1 over 1 plus theta times x. Because 1 over 1 plus theta less than or equal to 1 for x greater than 0, we get 0 less than or equal to ln of 1 plus x less than or equal to x. And for minus 1 less than x less than 0, we obtain x less than or equal to ln of 1 plus x less than or equal to 0. These inequalities are the basis for many error estimate proofs, such as bounding the remainder in a Taylor series. If the n plus 1th derivative is bounded by m on an interval, the Lagrange form of the remainder follows directly from the MVT applied to the nth order Taylor polynomial. Explanation. Typical exam questions ask you to locate the point c guaranteed by the MVT. Example 1. Find c for f of x equals x squared on the interval from 1 to 3. Compute the secant slope equals f of 3 minus f of 1, divided by 3 minus 1 equals 9 minus 1, divided by 2 equals 4. Set f prime of c equals 2c equal to 4, which gives c equals 2, and that lies in the interval from 1 to 3. Example 2, f of x equals e to the x on the interval from 0 to 1. Secant slope equals e minus 1, divided by 1 equals e minus 1. Solve e to the c equals e minus 1, giving c equals natural log of e minus 1 approximately 0.541, which is inside the interval. The procedure is always, first compute the average slope, second set it equal to f prime of c, third solve for c and verify it lies between a and b. In differential equations, the mean value theorem helps prove that a solution to an initial value problem is unique when the right-hand side satisfies a Lipschitz condition. Consider the ordinary differential equation y prime equals f of ty with y of t sub 0 equals y sub 0, and assume absolute f of t y sub 1 minus f of t y sub 2, absolute less than or equal to L times absolute y sub 1 minus y sub 2, absolute for all t in an interval. Suppose y sub 1 of t and y sub 2 of t are two solutions. Define g of t equals y sub 1 of t minus y sub 2 of t, then g of t sub 0 equals 0 and g prime of t equals f of t y sub 1 of t minus f of t y sub 2 of t. By the Lipschitz bound, absolute g prime of t absolute less than or equal to L times absolute g of t absolute. Apply the mean value theorem to g on the interval from t sub 0 to t with t greater than t sub 0. There exists c with g of t minus g of t sub 0 equals g prime of c times t minus t sub 0. Since g of t sub 0 equals 0, we have absolute g of t absolute less than or equal to L times absolute g of c absolute times t minus t sub 0. Repeating the argument or using Gronwall's inequality shows that absolute g of t absolute must be 0 for all t. That is, the two solutions coincide. An exam-type question often asks you to fill in the missing step or to justify why the mean value theorem can be applied to g, emphasizing the continuity and differentiability inherited from the original ordinary differential equation. Students often stumble on a few common traps. Forgetting the endpoint continuity, the theorem needs continuity at a and b. A function that is discontinuous at an endpoint cannot be used. Assuming differentiability at the endpoints, only interior differentiability is required. Demanding f prime of a or f prime of b is unnecessary and can incorrectly lead to no c. Thinking c must be the midpoint, the theorem only guarantees existence, not location. C can be anywhere in a to b. Mixing up Rolle's theorem and MVT, Rolle's theorem is a special case when f of a equals f of b. Many students try to apply Rolle's directly when the endpoint values differ. Ignoring domain restrictions, for functions like ln of 1 plus x, the interval must stay inside the domain x greater than -1. Keeping these points in mind prevents loss of marks. Question 1. Let f of x equals x cubed minus 3x on the interval from 0 to 2. Verify the mean value theorem and find a value of c. Solution: f is continuous and differentiable everywhere. The secant slope equals open parenthesis f of 2 minus f of 0 close parentheses divided by 2 equals open parenthesis 8 minus 6 close parenthesis minus 0 close parenthesis divided by 2 equals 2 divided by 2 equals 1. Set f prime of c equals 3c squared minus 3 equals 1, which gives 3c squared equals 4, so c equals the square root of 4 over 3, approximately 1.155, which lies in the interval from 0 to 2. Answer: c equals the square root of 4 over 3. Question 2. Prove that for any x in the interval from 0 to pi over 2, the inequality sign of x is less than x holds using the mean value theorem. Solution: take f of t equals sign of t on the interval from 0 to x. By the mean value theorem, sine of x minus sine of 0 equals cosine of c times open parenthesis x minus 0 close parenthesis for some c in the interval from 0 to x. Since cosine of c is less than 1, sine of x equals x times cosine of c, which is less than x. Answer: inequality proved. Question 3. Uniqueness. Consider y prime equals y squared with y of 0 equals 1. Show that any solution is unique on an interval containing 0. Solution: the right-hand side f of y equals y squared satisfies the Lipschitz condition on any bounded set. The absolute value of y1 squared minus y2 squared equals the absolute value of y1 minus y2 times the absolute value of y1 plus y2, which is less than or equal to L times the absolute value of y1 minus y2, with L equals 2 times m if the absolute values of yi are less than or equal to m. Apply the argument in topic 7. Assume two solutions, form their difference g of t, apply the mean value theorem to g, obtain g of t equals 0 for all t. Answer: the unique solution is y of t equals 1 divided by open parenthesis 1 minus t close parenthesis on the interval from -infinity to 1.